Actually, thanks for the invitation. I don't get to proselytize very often, so that's what I'm going to do for the next few minutes. Actually, just pharmaceutical sciences, just to give you a broad brushstroke, is a very broad field with 3 or 4 disciplines in it. It contains medicinal chemists and pharmacologists who discover new drugs. It contains pharmaceutical engineers who actually design new dosage forms, whether the pill has to be in a capsule or as a tablet or a patch, that sort of stuff. They tend to be very chemically engineered oriented. And also toxicologists who look at the adverse effects of drugs. It turns out in the grand scheme of things that taking a prescription drug is one of the most dangerous things you can do. They're a prescription for a reason. If they were safe, they'd be over the counter. And so there's a lot of toxicities associated with prescription drugs, and people who are experts in toxicology think about that occasionally at least. So I'm just going to focus on toxicology, but I'm going to take a broader perspective. I'm just going to talk mainly about pollution at the end of this talk, but really just talk about toxic chemicals and health and how it is that chemicals influence your health and the way that scientists go about assessing these sorts of effects. We need to consider all of this, though, in a social context, because obviously this is a hot button issue. Everyone's got perspectives and ideas about toxic chemicals and pollution. And so as scientists, if we want to be effective in a global perspective, we really need to understand the societal context. So I'm going to talk about that first. I'm probably standing in front of this. And then I'm going to talk about just some of the fundamental principles of toxicology and the way that we think about toxic chemicals. Give you a little talk on the history of toxicology, really because some very old examples give us some very modern concepts. And then wrap it all up back with the fundamental premise of what we're doing. Okay, sure, why not? So just in terms of broad brushstrokes, one of the fundamental problems in dealing with toxic chemicals is that most people have a very inappropriate, incorrect perception of chemicals and what they do. I'm not saying chemicals are safe, because they're not. That would put me out of my job, I guess. But our perception is really not very close to reality. And that gets to be a problem if that issue extends up to the government, because quite often what we do is we divert resources away from other causes. I mean, we could spend $100 million to clean up a landfill and clean up the water supply with zero effect on public health. And there really would be a lot better places to invest that $100 million. So toxicology could be thought of a way of prioritizing the things that society does, okay, into the most important issues. One of the reasons that there's this disconnect between perception and reality is that there's a disconnect between science, between journalism, and government. And this is very hard to overcome. They certainly aren't the same. They're coming from people in those 3 fields are coming from entirely different perspectives. Scientists are pretty good at dealing with data and pretty awful at communicating to the general public. Time will tell if I can avoid that. But it's really a hazard of the scientific profession. We lapse into jargon. We lapse into things that sane people think are trivial, but we think tend to be very important. So it's very difficult for scientists to commute to the general public. Journalists don't understand science as a rule. They're pretty good at communicating, but if they don't understand what they're communicating, it doesn't matter because they're not putting forward the truth. And I might posit the idea that in order to really understand the bottom line on a toxic chemical issue, you have to understand the fundamentals of the science. Otherwise, you won't be able to get to the essentialities of what's going on. And last but not least, there's government, which can or cannot be functional, depending on who's in Congress, I suppose. And the thing that we need to understand in this area, though, is that government policy is not science. Government policy on toxic chemicals is not based on science. It's based on policy. So they follow the laws of man and the laws of Congress, but not the laws of nature. And if the government says something is safe, that's actually not right, okay, because nothing is safe. We'll talk about that. And the government may say that there's an exposure guidance of 2 ppm, and you might think you're going to die if you're exposed to 2.1, or you'll be safe if you're exposed to 1.9. Nothing could be further from the truth. And even that magic 2.0 number was based on policy and not science. So there's these huge disconnects between these three areas, which oftentimes becomes quite problematic. Added to that is just the way that humans perceive these issues and deal with these issues. I think most of us have got this sort of angst and underlying feeling that we're poisoning the planet. Right? I think that I'm seeing some nods. Right? Of course, the issue is that since the advent of the chemical revolution, life expectancy has gone up 10 or 20 years. So how is it that life expectancy has gone up if we're poisoning the planet? Right? That's a bit of a disconnect. I'm not saying that we don't have pollution problems, we do, but it's not likely that we're poisoning the planet with anything except maybe CO2 and global warming. Okay? So that concept is fundamentally wrong. We could take that to the next level. I mean, I could name the 6 things which are responsible for 90% of premature deaths. If I think I can get them in order. It's smoking, overeating, alcohol, lack of exercise, not wearing your seatbelt, and one other that I can't remember. None of those are pollution, right? Some of those are toxic chemicals, cigarette smoking and alcohol, but that's all self-inflicted. So toxic chemicals and the general pollution in the environment is not having huge effects on causing premature death. It is causing adverse health effects, particularly in some circumstances, but not at the sense that it's threatening the entire planet. Now, don't mind to be implying that it's ethically appropriate to have unhealthy levels of pollution. I'm not. I'm just trying to get this into the context of overall health of people. There are 2 types of effects of toxic chemicals that people really worry about the most. First is cancer and the other is birth defects. And the reasons for that are pretty straightforward if you think about it psychologically. None of us wants to die of cancer. We dread it, right? It's long, it's painful. We really are fearful of it. So we have a heightened sense of the importance of chemicals that might cause cancer. Carcinogens is the word for that. We have this same sort of heightened sense for birth defects, and this is just tied up in the innate preservation of the species. Those of us who are parents know we worry more about the health of our kids than ourselves, right? And this is just all preservation of the species, and this gets all tied up into birth defects. I know if I'm walking into a public forum and I have to deal with a chemical that's cancer-causing or birth defects, there's going to be a lot of outrage in the audience, just because of this basic tenet of human nature. The other way that our brains are wired in dealing with these issues is we view it as a threat, and we respond out of fear rather than knowledge. And this is just innate. This is typical human behavior. If you're out swimming in the ocean and you see a fin coming towards you, you don't swim to it to see if it's a shark or a porpoise. You get out of the water, right? Yet this is just self-preservation. That same neural pathway is hooked up when you're talking about toxic chemicals. So you're responding on a self-preservation and actually out of fear rather than trying to find the ultimate truth. And this has led to a lot of misperceptions. I mean, people probably think that landfills are very dangerous and that automobiles are safe, and actually the exhaust out of your automobile causes a lot more health effects than landfills. That's just the bottom line on that one. People are worried about residues in food and pesticide residues causing nerve damage. Well, actually, mercury in fish causes more nerve damage than pesticide residues in food. So this gets more to be with our fear versus knowledge and some of our misperceptions about what's going on. So toxicologists try to look at these sorts of issues in a very systematic and objective way and define the effects of toxic chemicals. And we do this from a different set of conceptions than most people have. Most of us are sort of brought up to think that natural chemicals are safe and natural ingredients are safe, right? Look at TV, right? Did your mother ever tell you don't eat the berries in that bush because you'll get sick? Well, how could it be that natural chemicals are safe if you can't eat some of those berries, right? Because natural chemicals aren't safe. In fact, in terms of potency, some of the most potent toxic agents known to man are actually natural chemicals, not man-made. The other thing to keep in mind in this context is we evolved in a chemical soup. And we evolved protective mechanism against toxic chemicals. Otherwise, we would never have survived as a species. So we actually are fairly resilient in that regard. So it simply is not true that natural chemicals are safe. They actually can be quite dangerous. It's actually true that nothing is safe. Everything is dangerous. Everything is toxic, right? It's not an absolute black or white. It's a shades of gray. So we shouldn't be talking about whether something is safe or whether something is dangerous. We should be talking about the risk. How dangerous is it? What's the likelihood of harm occurring in a specific circumstance? The likelihood of harm is going to depend on the circumstance. And that's where knowledge of the toxicity of the chemicals really becomes important. Okay. Oops. Okay, let's go down one. Or not. All right, so who wants to play with this while I keep babbling away? So we actually, when we're defining the toxicity of a chemical, it really is frozen. When we're defining the toxicity of a chemical, it's really not too difficult. We try to do two things as toxicologists. We try to find out what does it do and how much does it take. And it's no more difficult. Are we back on track here? Okay. It's no more difficult than that. Okay. What does it do and how much does it take? We use fancy terms to describe that. So what does it do? We use terms like toxicity or hazard. And we're just trying to find out what is the worst thing a chemical could do? What's the whole spectrum of things that it's capable of causing? And so we dose animals, if we're doing this in an animal study, we dose animals with very high doses of chemical because we're not trying to ask what's the risk to a human in a given situation. We're trying to define all the sorts of things that the chemical could possibly do. We're just trying to define the what, not the how much. We do those in those infamous cancer bioassays that you might have read about, those 2-year feeding studies where we stuff animals full of whatever. And we try to determine whether or not it causes cancer. And these are widely criticized because the doses have no relevance to what humans are exposed to. But people who make those criticisms are actually ignorant of the goal. The goal is not to define what's going to happen in a given exposure scenario. The goal is to define what's the chemical capable of doing. Not all chemicals are capable of causing cancer. Some are, some are not. And we need to know that. That's the first thing we need to know is how much does it take. The next thing we need to know is, we need to know what the chemical does. The next thing we need to know is how much does it take. We need to know the dose-response relationship. We need to know how much does it take because then we can calculate the risk. And the risk is what is the chances of harm in a specific circumstance. The risk depends on the dose or the exposure intensity or something of that nature. It depends on how much you're exposed to, right? And how much you absorb into your body. And the risk is fundamentally different than the toxicity. You may be exposed to a carcinogen, but have virtually zero chance of getting cancer because of that exposure because the doses were so low. So we need to define the dose relationships so that we can actually calculate the risks. A more simple analogy is, let's say you have a cold, and so you take your 4 Tylenol, you take your 2 Tylenol 4 times a day for a week. So you take 56 Tylenol and you're fine. You don't have a headache for a week at least, right? And you go on your merry way. If you took those 56 Tylenol all at once, what do you suppose would happen? You would die, right? So there you go, right? The dose makes the poison. And so we need to be able to do that when we're taking these high doses in these animal experiments aimed at defining the potential for harm and then actually calculating what the absolute risk is. Okay? So there can be chemicals with great potential for harm, but there's little risk because the exposures were so low. How is it we try to define these things? Well, we can try to do it with human studies by looking at health effects in humans and seeing if it correlates with pollution or doing these sorts of things. These are epidemiologic studies. You have to realize, though, that if we see something in an epidemiologic study, the horse is out of the barn, right? It's already too late, right? Because the chemical is producing health effects. The idea is to study the health effects or the potential toxicity of the chemical before it's released into the environment so that we can prevent any sort of effects in humans. And the only way we can do that is to do animal studies. So we do animal studies. At the end, we can talk about the ethics of that or not. That's a different question. I can tell you they work. They're predictive. Okay? So if the end justifies the mean, so then that's why we're going to do animal studies. But we're left with some complicating factors. Usually we have to use high doses in animal studies, so we have to extrapolate from high doses to low doses. And we also have to extrapolate from animals to man. Okay? So it's not perfect. And any trained toxicologist will tell you it's not perfect. We never said it was perfect. It was not designed to be perfect. What toxicologists are trying to do is to create a safety net. We're trying to identify as best we can hazards before people are exposed to them. And we have a pretty good safety net, but it's not perfect. Things do fall through the safety net. Okay? You get into sort of a risk-benefit of how many studies do you need to do to be reasonably certain that there's not a chance of harm. Okay? So it's a safety net, and we do recognize that there's going to be some unexpected responses that were not necessarily predictable. But when we're doing this, the toxicologists are really driven by two things. We're driven by the knowledge that all things are poison. This is actually a quote from the 16th century. Everything is toxic. All things are poison, and the dose determines the risk. Okay? Those are the critical things that drive the conceptual process of toxicologists when we're studying the toxicity of chemicals. These are new concepts, like I said, the 16th century. None of this is very new. Okay? So what I'm going to do now is to go through some specific examples highlighting the principles of modern toxicology that they describe. And I'm going to do it in historical order, okay, just because it seems convenient. And the first that I'm going to talk about is Hemlock, okay, and Socrates. You know that Socrates was a professor, and he was corrupting the minds of the youth, and therefore he was sentenced to death. And how are we going to kill Socrates? We're going to give him hemlock, so we're going to give him a poison. You know, we still do the same thing, right, except we inject it. You don't take it orally, and it's a slightly different set of poisons, but they actually work at the same target in the body. So they sentenced him to die by the cup, okay? And the poisoner, this was a profession back then, the poisoner then knew how to make this lethal concoction. And I have all these papers because I got quotes here. So what happened when Socrates died is Plato was there and he wrote down what happened. Okay? So this is Plato, and all except for one Greek name, I can pronounce all of this. So, and this is how he described Socrates' death. So when the fatal cup was brought, he asked what was necessary for him to do. Nothing more, replied the servant of the judges. Then as soon as you have drunk the draught, walk about until you find your legs become weary, and afterwards lie down upon your bed. So the poisoner knew what was going to happen. Okay. So Socrates took the cup without any emotion or change in his countenance, and looking at him in a steady and assured manner, "Well," said he, what say you we make of this drink? May we make a libation out of it?" He wants to share this with everybody. And upon being told that there was only enough for one dose, so the poisoner knew how much it was going to take. Okay, at least, said Socrates, we may pray to the gods as is our duty and employ them to make our exit from this world and our last stage happy, which is what I most ardently beg of them. Having spoken these words, Socrates remained silent for some time, and then he drank off the whole draught. After reproving his friends for indulging in loud lamentations, he continued to walk about as he had been directed until he found his legs grew weary. So you see, the poisoner did know what was going to happen. And then he lay down upon his back, and the person who administered the poison went up to him and examined him for a little time, his feet and his legs, and then squeezing them strongly, asked whether he felt them. Socrates replied that he did not. Okay. He then did the same to his legs, and proceeding upwards in this way, showed us that he was cold and stiff, and he afterwards approached him, and he said to us that when the effect of the poison reached the heart, Socrates would die. And now the lower parts of Socrates' body turned cold, and when he was uncovered, his last words were, "Crito, we owe Asclepius a cock. Pay the debt and don't forget it." Okay? So Socrates' mind is working perfectly well during this whole little exercise. "It shall be done," replied Crito, "but consider whether you have anything else to say." Socrates replied in the negative, but was in a short time convulsed. The man then uncovered him, his eyes were fixed, and when Crito observed this, he closed his eyelids and his mouth, and Socrates was dead. Okay. So that's what happened during the poisoning of Socrates. And there are a lot of things that we can learn about modern toxicology from that. One is, as I highlighted, one dose was enough, right? So the poisoner knew the dose-response relationships. He didn't want to waste this stuff, though it's pretty easy to get, right? But he knew exactly how much it was going to take. So he knew the dose-response relationship. The poisoner also knew the toxicity. He said exactly what was going to happen. He said that your legs are going to become weary, and he said when the effect reaches your heart, you're going to die, and that's exactly what happened. So the toxicity was fully defined. Okay. What's going on here is that there's a specific chemical in hemlock, conine's the name of it, and it poisons your nerves, actually the junction between your nerves and your muscles, and it paralyzes you. And what happens is it starts in your periphery and comes to your core. And that's why his legs became weary, because it was starting at his longest nerves, coming back up. And when it poisoned the nerve muscle junction in his heart stopped beating. And the convulsions were subsequent to that. Okay. So we know exactly what's going on. It's a nerve poison. It's acting very specifically. If you think about this, Socrates drank this. So the first organ that saw the hemlock was his stomach. But it didn't injure his stomach. It didn't injure his intestines. It injured his nerves, and it started in his toes. All right, so it acts very specifically distant from where it was absorbed. Okay. And also, it's a nerve poison, but Socrates had his wits about him. He's saying paying off the debt for that cock, right? So it's so specific that it's hitting the nerves in the periphery, but not the nerves in the central nervous system. So it highlights how specific chemicals can act, okay? Because the response to a chemical is usually due to a molecular interaction of a toxic chemical with a very specific target in the body. Okay? So we now know that chemicals act very specifically, which is why we define the toxicity of a chemical. So the story of hemlock actually continues. Hemlock, it turns out, is very poisonous to humans, but it's not very poisonous to birds. Birds actually have got defense mechanisms against this chemical, and they're very impervious to it. If you think about this in evolutionary terms, it's actually not much of a surprise. You know, in the planet, there is chemical welfare going on between all the organisms in the planet. Plants are synthesizing extraordinarily toxic chemicals to ward off predators. Predators are evolving protective mechanisms so they can go eat that plant, right? And so we really have got chemical warfare going on. And there are some extraordinarily toxic chemicals that are present in plants. Conine is one of them, and it's in hemlock. But birds are insensitive to it, as I said. So now you can imagine this scenario. What do you suppose would happen if birds gorged themselves on hemlock and then were killed and we cooked them and ate the bird? There could theoretically be enough hemlock or conine in the bird's muscle that we would ingest a lethal dose of hemlock by eating a bird that had engorged itself on the hemlock. And that actually has happened. So I'm going to read from the Bible. This is from the book of Numbers, chapter 11, verse 31 to 33. So, then a wind from the Lord sprang up. It drove quail in from the west, and they were flying all around the camp for a day's journey, 3 feet above the ground. The people were busy gathering quails all that day, all night, and all the next day, and every man got at least 10. They spread them out to dry all about the camp, but the meat was scarcely between their teeth, and they had not so much as bitten it when the Lord's anger broke out against the people, and he struck them with a deadly plague. And the deadly plague was conine from all of the hemlock that the quails had eaten. That's a picture of a quail. So the idea here, pardon?
It was last week's Torah reading.
Oh, there you go. There you go. All right. All right. So there are a lot of important lessons in here. First is that chemicals can move in the environment. Right? So this chemical was in the plant, but a bird ate it, and toxic levels built up into the flesh of the bird. And we see this sort of thing happening all the time. Rachel Carlson's Silent Spring DDT was planted on the fields. It washed off into the watershed. It was bioaccumulated in the fish. Eagles that ate the fish were poisoned with DDT. I'll talk about mercury later on. It's happening right now. The other thing that this points out is species sensitivity. There's a lot of difference in the response of one species versus another to a toxic chemical. If we were doing toxicity testing on conine, for the sake of argument, and we picked quails as our test species, we would have missed the boat. Right? We would say this stuff isn't very poisonous at all. People can take it with impunity. We would have been dead wrong, literally. So the idea is that you need to be very careful when you're examining the toxicity of a compound in a species other than man, and you need to interpret it very properly. We actually know enough about the effects of chemicals, we can make reasonable predictions about species sensitivity and make those extrapolations appropriately. But they still are extrapolations, so we need to be careful about that. Now we're going to move ahead by, probably 1,000 years, and we're going to talk about arsenic. Okay. Arsenic is another naturally occurring chemical. It's, I don't know, 0.1% of the Earth's crust, something like that. It's very toxic. A 1/10 of a gram is lethal in humans. It has no odor and no taste. Boy, this is good. Sherlock Holmes would like this one, right? And it also produces delayed death. So you can put it in someone's drink. They won't know it's there. There's no way of detecting it. And they're going to die a day or two from now. So you can plot your escape. So it's a wonderful way to kill people. Okay. And as you probably know, that's what was happening. It was the poison of choice. The way it kills people actually is it works in a very specific protein in your intestines, and it prevents water absorption. So what happens is that you die of massive, massive diarrhea. Okay? So, pardon the French, you shit your brains out. In essence, what happens when you just massive diarrhea and you die of dehydration and cardiovascular collapse. Very different than conine, right? It's acting in a very different place. The other thing that about this is it looks exactly like cholera. Now, we don't have much cholera now, but in the Middle Ages, cholera was rampant. And there was absolutely no way to tell if a person was killed with arsenic or whether they got cholera. And the general concept here that's important in this regard is that this holds true today. If we have a toxic chemical in the water supply that slightly increases the incidence of a very common disease, we'll never be able to tell, ever. There's too much noise in the system, we just can't tell. On the other hand, if a chemical produces a very specific effect, we'll see right away. But an air pollutant that increases lung cancer a little bit, we'd never be able to figure it out by looking at human data because there's too much noise in the system. So in essence, that's what's going on with arsenic poisoning here. We couldn't discriminate that from cholera. Okay? So people were dying right and left of cholera. Okay? It turns out that you could give arsenic in a variety of ways. So you can put it in someone's tea, like arsenic and old lace, right? And you swallow it and it'll kill you. You can actually inhale it and it'll kill you through the same mechanism because it's absorbed through your lungs, gets to your bloodstream, goes down to your intestines and produces its effects in the intestines. Doesn't injure your lungs, does nothing in your lungs. It just hits your intestines. And to me at least, the most fascinating murder with arsenic was actually Pope Clement VII, where the cardinals wanted to do away with him, and he had to lead a procession down a long aisle. So they gave him a candle that was laced with arsenic, and the candle burned and it vaporized the arsenic, and he inhaled it, and a day later he died of cholera. It's the most remarkable thing. Okay, so you can do it by inhalation, and it's lethal. On the other hand, you can paint it on your skin and it doesn't do anything. It's safe, theoretically. And the reason for that's probably pretty obvious. It's not absorbed across your skin, so you can do that with impunity. So in the Middle Ages, in Italy, they had something called acqua tofana, which was this little liquid arsenic preparation, which young women could buy to clear up their complexion, because it worked. And the real handy thing is you could put a couple drops in your husband's tea and you become a rich widow very quickly after that. And there was no way to tell. Okay? Colorless, odorless, tasteless, looked just like a common disease. So this occurred for hundreds and hundreds of years until around 1836, to be precise, when someone named Roger Marsh discovered an analytical technique to measure arsenic in blood and urine. And all of a sudden, you could tell if someone was poisoned with arsenic because you could measure it. It turns out that it's in a lot of your body parts. It's in your blood, it's in your urine, it's in your fingernails if you live long enough, it's in your hair because it sticks to the proteins in your hair when you're making your hair. So you could take virtually any tissue and measure it for arsenic. And there have been a variety of times when they've actually done that. They took a locket of Napoleon's hair to find out if he was poisoned with arsenic. He wasn't. They did the same with William Henry Harrison. They actually exhumed him because they thought he might have died of arsenic poisoning. He didn't. He actually died of cholera. But you can do this through this modern analytical toxicology. And so so you got someone dead to rights. Right. Someone's dying with the symptoms of arsenic poisoning and they've got high levels of arsenic in their blood, right? You know it, right? You know why they died. We can sort of turn this around now in other contexts. So let's take a urine sample from somebody and we find marijuana in it. I think they smoke something, right? It's there, right? You can't argue your way around this one, which I tell my students all the time, just own up to it, right? That's just analytical toxicology used in another way. Or in another circumstance that we'll talk about, you might think that a lot of people were poisoned with something. Well, let's just measure their blood and see if it's in their blood. If it is, they were poisoned with it. If it's not, they weren't. All right, pretty straightforward. And that's all analytical toxicology. That's all drug testing is. Same sort of thing. All lessons that we learn from arsenic. Now we can move forward probably about 100 years. We'll just talk about war gases. And the reason I talk about war gases is that they act in a different way. So I've given you examples of chemicals that interact with specific targets, and they're very organ selective and very specific. War gases don't work that way. These are the things that were invented by the Germans in World War I, and they're still used in the Middle East. And these things injure the first tissue they come in contact with. They're very reactive. They don't get anywhere else. They're not absorbed. They're all consumed as they're reacting with your tissue. And so they only act at the site of contact. That is how they work. And so, especially with the war gases, if you got it in your eyes, it would destroy your eyes. If you inhaled it, it would destroy your lungs. If you got it on your skin, it would burn your skin. It's like a chemical burn, and it burns whatever tissue it comes in contact with. This is pretty insidious stuff. This is not one of the greater chapters of mankind using these weapons. Probably the most famous person that was exposed to war gases was Adolf Hitler in World War I in the trenches. So I happen to have Mein Kampf right here and describe what he said about it. So in the night from October 13th to 14th, the English began to throw gas on the southern front. Yellow cross gas was being used, which is nitrous mustard, the effects of which were unknown to us as far as personal experience was concerned. I was to get to know it personally on this very night. On the eve of October 13th, on a hill south of Wervik, we had come under a drum fire of gas shells lasting several hours, which continued more or less violently throughout the entire night. Towards midnight, a part of us passed out, some of our comrades forever. They were the lucky ones, probably. Towards morning, I too was seized with pains, which grew worse every quarter hour, and at 7 o'clock in the morning, I stumbled and tottered rearwards with burning eyes, but taking with me my last report in the war. Already, a few hours later, my eyes had turned into burning coals. That's what these chemicals do, okay? It had become dark around me. He actually was blind for several weeks, okay? And then he was taken to a hospital in Germany, and he eventually recovered. So these chemicals it's a chemical burn. They destroy any tissue in which they come with contact. Okay? This sort of effect does not occur only for war gases, but other things as well. There are a lot of direct-acting chemical carcinogens, and they cause cancer because they act with DNA and cause mutations, and ultimately that can grow into a tumor. They're direct-acting, and they actually injure the tissue in which they come in contact. So in an experimental study, if you inject it in the back, an animal will get a skin tumor in the back. If you make the animal drink it, they'll get a stomach tumor. If the animal inhales it, they'll get a lung tumor. So these things act just in the site of contact where the exposure concentrations are the highest. And that's one of the reasons why toxicologists are really very concerned about the route of exposure. So you might be in a circumstance where there's some chemical in the water and there's a lot of data which says it injures the lungs if it's inhaled, and the toxicologist says, but we don't need to worry about it in the water. He or she's probably not lying, right? Because it's a site of entry sort of thing, and the route of administration is very, very important. So we have to be careful when we design animal studies that we look at the right route of exposure. And we don't want to expect a priori that a chemical in the drinking water will produce the same effect as if it were in the air, because it could be very different. Okay. So those are just things that we need to take into consideration. Probably the seminal event with respect to the toxicity of drugs was thalidomide, which many of you may know about or remember. This was a drug that was given to pregnant women, and it causes the arms to develop poorly. So these babies are all thalidomide babies, and their entire arm, both the top and the bottom of their hands, is only about this long. So the shafts of the arms didn't develop. If you're sort of curious, what happens is it prevents the growing of the blood vessels down the shaft so that you can't have a long extremity being developed. Okay? So that's actually how it's working. So this was a very unusual event. Right? This is not like cholera. This was pretty unusual. This malformation was unheard of. And it was quickly discovered what was the cause, and it was removed from the market. Quickly, took 4 years. That's pretty quick in the grand scheme of things. And this was all the result of a single physician in a clinic in Germany. And the first year he saw one case and he thought it was sort of interesting. The second year he saw a second case, and then a third, a fourth, and a fifth. I think he had 6 cases, and he knew there was something going on. And the third year was like 160 cases in his clinic. They figured out what it was, and the next year it was down to 0. So this is all a very specific effect produced by thalidomide. It turns out that there's a very critical window for producing these effects, and the effects of thalidomide depend on the day you're taking it. If a pregnant woman took it on day 23 to 25 of pregnancy, there were shorter missing arms. If they took it later, there were shorter missing legs. And if they took it even later, the arms and the legs were okay, but the fingers were shortened. Okay? So the precise effect depended on the day in which it was administered, and that's called the critical window. This is true for virtually all chemicals that cause these sorts of structural malformations. There's this critical window, and the day in which you take it is absolutely important. One of these chemicals that do this are called teratogens. Terato is monster and generate, so they're called teratogens. There are a variety of known human teratogens. Vitamin A is one of them, so is vitamin D. Natural chemicals are not safe. And even with vitamin A, the effect that's produced depends on the day in which it's taken. And in fact, we know from case reports that taking a huge overdose of vitamin A on one day of pregnancy is enough if it's the right day. Okay? So there's these very sensitive windows. The way that this lines up, thalidomide's a good example, is if the woman happened to take thalidomide the day that the arms were developing, then there would be a defect in the arms. If she took it the day the legs were developing, there would be a defect in the legs, but not the arms, because those happen on different days. So these teratogens tend to act during organogenesis, when the organs are being formed. The first part of laying down an organ is to put down the scaffolding or the connective tissue, and after that the organ just grows. And teratogens work at that very specific step. So they're very, very sensitive on the time of gestation. The scary thing is that organogenesis starts about day 21, and that's post-conception. So the most sensitive period of humans to teratogens is day 21 to day 33. A woman's period is only 7 days late. She doesn't know she's pregnant, and she's already into that critical window, which is sort of one of the reasons why one should see their obstetrician right away, to be careful for these sorts of things. So these events can occur before women even know they're pregnant. How did this happen? Obviously, there was a failure of that safety net, right? The toxicity of thalidomide was tested. They weren't wholly irresponsible. It was tested in rats, and rats are impervious to the effects of thalidomide, just like quails are impervious to the effects of conine. So they looked at the wrong species. It was perfectly clean. After the event, when they went back, they looked at another species. They looked at rabbits, and rabbits reproduced the human effects beautifully. So we missed it because we only looked at one species and we didn't pick the right species. So we wrote new laws. So now birth effects of any new drug, you need to look at the potential for birth effects in at least 2 species of animals, one of which is not a rodent. So usually studies are done in rats and rabbits. Okay? The laws don't require 5 species, they don't require 7. We're just talking about how good does that safety net need to be. Okay, so 2. Doesn't require monkeys, okay, right? So just 2. And things look like that we're okay, that we're catching most anything. If you ever look at the labels on a drug, they almost all drugs say safety in pregnant women has not been assured. Right? That's what this is all about. Right? We've tested in a couple of species, and there doesn't look like there's an effect, but we can't be absolutely certain. One of the toughies with drugs right now is, should thalidomide be totally banned, or should we allow it under prescription sales for other uses? It turns out that it's really good at preventing some forms of blindness, because some forms of blindness are due to too many blood vessels growing in the back of your eye, and that's what thalidomide prevents. And so it is on the market for the prevention of blindness. Okay? The idea is that it's a prescription drug and no one else will be taking your pill, right? Because it's given specifically to you. That doesn't always happen, right? And so that's actually a source of great concern. But it really highlights, don't take anyone else's drugs, right? That's really a crazy thing to do. And also highlights the fact that prescription drugs are dangerous. As I said before, that's why they're prescription. Okay? They have serious side effects. It is perfectly legal to have a known human teratogen be on the market as a prescription drug. There are a lot of them out there. Okay? They're just with warnings and they're only by prescription. Simple as that. Okay? So you really need to pay attention to all of those things. We're winding our way through here, so I'll just talk briefly about modern nerve agents. So we killed I didn't, but they killed Socrates with a nerve poison. The Army still uses nerve poisons. They don't use cyanide anymore. That takes 5 minutes, and there's plenty of antidotes available. What they use actually is something called saxitoxin. It's a poison made by plankton, okay, in the ocean. It's a natural occurring thing. And this is what Gary Powers had with him. Now, those of you may know, back in the 1950s, we flew surveillance missions over Russia. This is an active war, right over Russia. And Gary Powers' plane was shot down over Russia. This was in the last few months of Eisenhower's presidency, and he tried to deny that we were doing this, but they had Gary Powers. So, it was pretty clear what was going on. So when the KGB got him, they emptied his pockets, and they discovered he had a quarter in his pockets, and it looked a little funky. So they looked at this quarter and they split it open longitudinally, and inside this quarter was the head of a pin. And they said, So they took the head of a pin and they jabbed it into the German Shepherd that was right there. The Shepherd was dead in 2 seconds. That was saxitoxin. Lethal dose on the head of a pin. It's a perfectly naturally occurring substance. It's a nerve agent. It paralyzed the dog in 2 seconds. It took 2 seconds to get absorbed. And that was the delay. That's how quickly some things can work. Okay? It's a couple millionths of a gram is enough to kill people, and I won't tell you how many tons of this stuff is stored in Colorado. Okay, just in case the Army needs it, I think. So nerve agents are a really good way to kill someone pretty quickly. They're actually pretty prevalent. And there are some natural ones that are extraordinarily potent. I'm just going to talk about Agent Orange really briefly. I think we all know that there's this huge controversy about Agent Orange, and it's causing all these health effects in the Vietnam vets and the ground troops. So they did an analytical toxicology study. They collected blood and fat samples from Army vets, and guess what? There was no Agent Orange in them. And the reason is because the Agent Orange, it was a contaminant in the Agent Orange causing the dioxin, causing the health effects. That was all sprayed in the early 60s, and most of the vets were there under Richard Nixon in the late 60s and in the 1970s. They weren't exposed. So all of that hullabaloo in the papers was pretty much nonsense because they weren't exposed. They didn't have any. It was in the dirt, but it's not absorbed across Army boots. And they weren't there long enough to actually develop significant exposures to this compound. That statement is not true for the Air Force people that actually sprayed it. They were exposed. They've got elevated tissue levels. They have health effects. But the general ground troops do not. And just highlights the difference between risk and toxicity. Dioxin is really dangerous, there's no doubt about it, and really toxic. But if you're not exposed to a significant amount, you're not going to have an adverse health effect. So that was probably the biggest circumstance where the press blew everything totally out of proportion. And Congress acted in response to the press, in response to policy, but not in response to science, okay? Simply because they weren't exposed. Okay? There's just no ifs, ands, or buts about it. The last thing I've talked about is mercury. This is a problem that exists today. It gives you an idea of some of the complexities of some toxic agents. On this slide, the reds are the states where they have advisories that you shouldn't eat the fish. You live in one of those states. I bet most of you don't know this. You probably shouldn't be eating fish you collect in local waters, okay, because of the mercury. This is the release of mercury into the air, and you can see Connecticut's right in the red zone. Where does it come from? The mercury comes from burning coal. And, all right, now we're doing the same thing again. And you want to come play with us again? It's released from smokestacks as mercury into the air. It then comes down with the rain into rivers and into lakes. The bacteria convert it to methylmercury. Fish, what did you do? You just played with that? Okay, what happens again? Okay. So it's converted to methylmercury. Small little beasties eat it, and small fish eat those beasties, and then medium fish eat the small fish, and big fish eat the big fish. And they accumulate more and more mercury in their flesh the longer they live. So in general, bigger fish live much longer than smaller fish, and so they've accumulated more mercury, and we're more concerned about the mercury in big fish than small fish. So there actually are eating advisories out by both the FDA and the EPA about tuna fish. We'll talk about that in a bit. You know, they're saying that you probably should only eat that a few times a week, if that much. If you're pregnant, probably not at all. Or versus sharks, pikes, or halibuts, maybe a few times a month. Okay. And the reason for this is because we're concerned about mercury. Like choline in the flesh of the birds, the fish seem to be relatively impervious to this mercury, and it's built up to toxic levels in their meat. Well, what does it do? I mean, it is a naturally occurring compound, mercury is. It causes nerve damage, yet another nerve poison. Okay? And what it does is it causes, the first studies were rats and mice, it causes damage in the peripheral nerves in their arms and their legs. It decreases the reaction times and their reflex times in mice. You don't tap the knee of a mouse, but you can look at their reflex times. And they're delayed, so we know it's causing some sort of neural things. It's of sufficient importance that we did it in monkeys. We don't test many chemicals in monkeys, but they tested it in monkeys and saw exactly the same thing, where there was decreased reflexes, there was decreased sense of touch, and the monkeys were having poor coordination and difficulty walking. If you can't sense when your foot hits the ground, it's difficult to walk. Do you ever have your foot fall asleep and try to walk when it was numb? Right, it's not easy. So that's what this peripheral neuropathy, peripheral nerve damage, is making it difficult to walk. And they also saw sensory deficits, changes in peripheral vision, some problems in hearing in monkeys. These were pretty low doses, and young monkeys in particular were sensitive, probably 10 times more sensitive than adults. That's sort of a general pattern. And certainly fetuses were sensitive. So mercury is something to be worried about. As a toxicologist, we would look at that and say, boy, it does exactly the same thing in rats and mice and the same thing in monkeys. I bet it'll do the same thing in humans, right? It's just one more mammalian species. And lo and behold, we know that it does exactly the same things in humans because we've been able to look at some specific populations of people who are exposed to high levels of mercury in their diet. There's so much mercury in the air that it's polluted all of the oceans. And all of the fish in all of the oceans now have some level of mercury in them. And so the studies that were first done were with indigenous populations. The first one was in New Zealand. These were populations that their sole protein source was fish, which they were catching from the ocean. And what they did was they looked at the incidence of these sorts of neural defects in children whose mothers were exposed to mercury. How did they know how much mercury the mothers were exposed to? Well, it's analytical toxicology. They measured their hair, right? Because it stays in their hair. And if you pick the right indigenous population, you go find an indigenous population where the women don't cut their hair their whole life, but they just let it grow. And we actually have analytical techniques that can take a single strand of hair and measure the mercury concentration as you're going down the hair and backtrack the woman's exposure for her entire life, or at least until she, last time she had her hair cut. Okay? And so that's what they did. And so they could backtrack. They took children who were 4 and they followed them up when they were 6, and they backtracked their mercury exposure in utero by looking at their mother's hair. And the higher the level of mercury in the hair, the higher were the deficits, the neurologic deficits that they saw. So what they saw in these children was slow reflex times, poor muscle coordination. Is this me? This is me. I'm almost done. Poor muscle coordination and problems with peripheral vision. Okay. Exactly what we saw in mice and rats and monkeys. The animal studies do work. Okay. They did the same thing in Quebec. They did the same thing in Iraq. Iraq is a circumstance way back in the 70s. They had a famine. The United States sent them a lot of wheat seed to grow wheat to make bread. The wheat seed was treated with mercury as an antifungal. The Iraqis did not plant the wheat seed, they ate it. And they were exposed to mercury by doing that. I mean, I think we were pretty dumb. Are starving people going to plant seeds and wait 6 months? I don't think so, right? So you have this little wave of mercury exposure, and they followed the women up using their hair, right? And the mercury levels in children during gestation, and they saw exactly the same things. They saw delay in walking, delay in learning to talk, and slow reflex times and neuromuscular problems. So in multiple populations, this has been shown. So this is just a rock solid case. Every animal model and human models, and we know the dose levels that are required to produce these effects. And so the question becomes, are fish safe? And the answer is it depends how much you eat, right? So you get back to this little warning, and canned tuna, if you're pregnant, actually the EPA will say once a week. You probably shouldn't have it more than once a week. The margin of safety is only about 3-fold, which isn't very much. So if you were to have 3 cans of tuna a week, you would probably be in the range where your child would have some subtle neurologic defects. Okay? So there really is an awful lot of mercury that is present in the food. Okay? So much so that we're taking action. So what should we do? I think it's pretty straightforward. We need to stop putting mercury into the atmosphere, right? Which means we need to stop burning coal. Now you understand the politics, right? We don't have the political will to do it, which highlights that science and policy are very different things. If you follow this at all, you know that Obama's getting lambasted by Congress for his mercury standards. He's trying to clean up the mercury emissions, and Congress will have none of it because he's starting a war on coal and he's going to destroy the US economy. Okay, welcome to America. Okay. But the science is pretty straightforward. And the science that I've sort of talked about is highlighting these things. Natural chemicals are not safe. Most of the things I talked to you about today actually were natural chemicals. They're simply not safe. Nothing is safe. Everything is toxic. We need to be talking about the relative risk. How dangerous is something? Okay? In order to do that, we need to know what does it do, what's its toxicity. We need to know how much does it take, what's the dose-response relationship, and then we can calculate the relative risk. What's the likelihood of harm occurring? As a toxicologist, that's when my job stops, right? I can tell you what the risk is and use all my fancy science, and I can even come up with numbers, right? But I can't tell you what an acceptable risk is. That's actually a society's decision, not a science's decision, determining what's acceptable and what's not. I can tell you that the philosophy that zero risk is acceptable does not work, right? Because everything has some risk. So you can't do that, okay? You're going to have to come up with some definition of things that are acceptable versus not acceptable. And with that thought, I think I'll stop, and we've got a couple minutes for questions, I think. I didn't, yep. Yeah.
I just want to let you know that I am from the EPA, and it's super fun.
Cool.
We do clean up landfills
Yep.
and harbors. And
Yep.
so,
And there's some bad ones in the Northeast.
So I just wanted to get that out there for the record that it seemed in the beginning that you were saying that all of the cleanup decisions, and you may not have been saying this, are based on politics and not science. And I would say that's not true.
And thanks for correcting me if I gave that impression. Right. It's a mixture of both. Absolutely. Absolutely. Right. Yeah.
I'm curious about mercury. Coming from the coal plants to the air, into the water, there's also mercury apparently that was used industrially in New England for processing, I think, beaver pelts and things.
Yep.
So you go to a seemingly pristine environment and there's mercury. Does
Right.
the mercury, if it's settled in the silt at the bottom of a pond or a lake, does that get into the fish, or is it more when it's en route from the smokestack to?
Well, there are some organisms that feed on the dirt in the bottom, and then it enters the food chain that way.
So if
So
we
it can.
regulated the coal industry and stopped that as a source, there would still be mercury in the environment.
I think the half-life's about 70 years. And so it'd take 200 years for the levels to go down fourfold. You might know that, what the half-life is. It'll take a long time. Eventually it'll go down. You're right, there are areas with very high concentrations because it was used industrially. And then there are more widespread areas because it's due to emissions from coal ultimately. Yeah?
You mentioned that sex toxin is stored in the water. Does the
Toxicity, yeah.
okay, does the toxicity level remain stable over time?
Yeah. If you store it properly. Yeah.
Unlike our pharmaceuticals and our medicine cabinets that,
They're actually
some of their effectiveness after time has passed.
correct. I don't know what the half-life of it is, but it's fairly stable. In the grand scheme of things, most medicines are stable for 2 or 3 years without any sort of special holding. That's a remarkably stable compound. Yeah.
Based on the fish timeline for eating them, it seems to me that mercury in the body has a faster half-life and moves through us faster than 70 years. If you can eat a fish once a week, it's going to be okay.
Yeah, I don't quite remember its half-life, but it is shorter than that. It takes about a month, I
Is
think.
there anything we can either eat or take concurrently with fish to either block uptake or maybe chelate it out of the body faster?
Boy, I don't think so because it's methyl mercury. Why expose yourself to another potentially toxic chemical? Yeah, well, actually, just eat it in moderation. Actually, to be honest with you, I wouldn't. If one were pregnant, they probably shouldn't eat canned tuna fish once a week. I mean, they shouldn't eat it every day of the week. Once a week is probably fine. But you shouldn't think that there's 100-fold margin of safety in that. There's not. So just everything in moderation. Yeah.
What is your opinion of organic food as far as the toxicity is compared to non-organic?
It's not as straightforward as some might purport. How's that? Can I get away with that, or do you want I can't give you I can tell you some of the general principles. I mean, many of these highly toxic compounds are made by bacteria and fungi, and that's exactly what pesticides are preventing from growing in the food. And so that you're actually ending up with a different distribution of chemicals in the food supply when we use pesticides or not. And so whether or not the potential for naturally occurring toxicants, outweighs the potential for the pesticides, I can't give you that answer. I can really say that it's not as straightforward as some might think. Yeah.
So you were talking about toxicology of chemicals individually. How does research into toxic interactions, is it performed in a similar method or?
So there are a variety of ways we can do that. Sometimes we look at the toxicology of mixtures, where we give mixtures on purpose. Another way we can go about that is if we understand how the agents work. We know that two agents that work through the same mechanism might actually add up together, and so we can do it on a mechanistic base. So those are the two approaches. There are 600,000 chemicals in commerce, of which we've tested 1,000, maybe 2,000. So I shouldn't be saying life is grand. But those are things that we're trying to do. For air pollution in particular, we're trying to do those sorts of assessments. So, yeah.
I hope this isn't too personal a question. I said, I hope this isn't too personal a question. How do you balance your personal ethics with the hard science, the hard data you get, versus what society through our government decides? At what point do you cease being, or can you cease being an objective scientist?
Boy, that's a toughie. I don't think I'll answer that directly, and maybe I'll babble my way into the answer to that one. Because I sort of look at the levels of something that's in the food or the drinking water, and I say, would I let my kids drink that without worrying? And if the answer is yes, then I believe my science, right? And lots of times we had a circumstance in my town in Ellington where we had something in the drinking water. And I sort of took that approach by going through the science. I believe in my science, but I also believe that, as I said, it's society's decision, it's Congress's decision, or it's the EPA's decision. I'm on a lot of advisory panels, and I talk to a lot of people in the EPA. I give them my 2 cents worth. Whether or not that changes anything, I guess I don't lose any sleep over that. I think I'm honor bound to say what I think the situation is, and then let other powers make the final decision. Does that sort of get at it?
I hope you can see it.
No. So, yeah.
As there's more options available, do you see a change in moving away from animal testing, or is that really looking to see this way to get the results that you see?
We're actually moving.
Repeat the question.
Oh, should we?
I asked if he sees any technology or moving away from animal testing, or if that's really the clear option.
We are moving away from it. As we understand more about cellular responses, we can actually do a lot of these initial studies in cell culture systems, even using human cells and not animal cells. And we can do a lot of the initial studies and characterization without using animals, and we're moving towards that very, very quickly. Are we going to get to the day where it'll all be removed? No, because if we have a chemical that is causing cancer in some cell lines but not others, we're probably going to need to do an animal study at some point. But we're moving very rapidly to get away from it. They're not perfect mimics in the first place, right? So we're not replacing something that's perfect. So, but there's a lot of effort to do that. And actually, in response to molecular biology and understanding how cells work. Okay, thanks.